This meeting is being recorded.
In section 4.9, we're going to discuss specifically now cyclic structures, cycloalkanes, and we're going to review both angle strain and torsional strain, and how some of these cyclic structures may have different 3D conformations that reduce some of this strain. So in our stereochemistry lab, we will specifically look at cyclohexane and different conformations and then different energies that result from adding substituents and whether they're in different positions. So let's take a look here. Let's start off and note that anything that's sp3 hybridized, we know, has an ideal bond angle of 109.5. So if you recall, right, we can think of methane here, right, as having these hydrogens as far apart from one another as possible. So in between, in a spherical type of scenario in 3D space, they would be about 109.5 degrees from one another. That would be their dihedral angle. So now, if we have cyclic structures, we can see these carbons are all sp3 hybridized, right? They all have these hidden hydrogens. So we are far from that 109.5 with cyclopropane, still pretty far with butane, cyclobutane, cyclopentane, getting even closer. And then we have some wider angles as well. So these are not near their ideal angles, and if these cycloalkanes remained flat, like we see in these images, they would also experience this angle strain that I just mentioned, due to not being near that 109.5. So this angle strain will be released by the structure kind of folding up or taking different conformations three-dimensionally. So let's take a look here at the combustion data. So we saw that when we had the energy released through heat of combustion, we could kind of see what was the higher or lower energy structure if we compared linear versus branched alkanes. We can also see that cycloalkanes follow a trend with combustion data, and the ring size is our factor that changes throughout our cyclic structures. So we see starting around here, around 5-carbon ring, and so we have a similar energy per CH2 group. So we'll break this down based on the energy, the combustion energy, the enthalpy values, and CH2 groups on the next slide here. Oh, no, it goes into further detail in the textbook. I apologize. But you can see this trend. So it kind of is as equal for every CH2 group in a structure that's between 5 and 12 carbons in length here. So let's look at this next slide. So say we have cyclobutane here. So cyclobutane is a 4-carbon structure in a cyclic in a ring structure. And if we look at the energy per CH2 group, we can see that cyclobutane per CH2 group has about 27 kilojoules per mole higher energy, so it's that much less stable than cyclohexane. And the reason that's attributed to this is because of both angle strain, where we have this 88-degree angle, dihedral angle here that's not that 109.5. And then we also have some torsional strain because these bonds are not fully staggered or eclipsed. So there's like a intermediate torsional strain, not as much as an eclipsed structure would be. But we can see that this puckered conformation shown down here is not flat, and it would have less torsional strain. The angle strain doesn't change too much, but the torsional strain will be reduced. We can see something similar with cyclopentane, but not as drastic of a structural change. Cyclopentane is only 5 kilojoules per mole less stable than our cyclohexane for every CH2 group. And notice that it has very little angle strain. It's almost that perfect or ideal 109.5, and it has very slight torsional strain as well. So it doesn't need to pucker or make quite as bendy of a structure. It can take on this envelope conformation. So that's what they're saying. This looks like down here, a type of envelope, to avoid most of those strains. So if we were to take a look at cyclohexane, we're going to see that there's many more conformations. So I'm going to reserve a full video for the conformations of cyclohexane, and we'll continue that in the next video.